Hi, it's Maria Gigauri and Tengiz Pataraia, and today we will speak about Yocto Linux. Yocto project is a cool open source community project that allows you to build your own Linux system from scratch to booting it into your embedded hardware, which makes embedded Linux simple and accessible. It helps developers create customized systems based on the Linux kernel by providing useful templates, tools, methods, and wide hardware architecture support on ARM, PPC, MIPS, x86. The purpose of Yocto project is to help you build a custom Linux OS for just about any kind of embedded computing device. Yocto can create Linux images for all the major hardware architectures. Yocto is essentially an umbrella project where the open source community and industry is coming together to collaborate on a set of tools and best practices for developing custom Linux images. The best part is that there are no software policies. Yocto has a high degree of flexibility and customization. Historically, the project grew from and works with the Open Embedded project, which is where the build system and some of the metadata are derived. Open Embedded's build system is based on bit-bake recipes, which specify how a particular package is built, but also include lists of dependencies and source code locations, as well as instructions on how to install and remove the compiled package. Open embedded tools use these recipes to fetch and patch source code, compile and link binaries, produce binary packages, and create bootable images. In order to go further, I want to clarify some important terms we will be using. Build system or bitbake is a scheduler and execution engine which parses instructions or recipes and configuration data. Recipe is the term you will come along a lot while working with Yocto. You can interpret those as instructions, as I mentioned before, and it is the most common form of metadata. Metadata is a key element of Yocto project. It's used to construct Linux distribution containing the files that build system parses when building an image. In general, metadata includes recipes, configuration files, and other information referring to the build instructions themselves, as well as the data used to control what things get built and to affect how they are built. The metadata also includes comments and data used to indicate what versions of software are used and where they are obtained from, as well as changes or additions to the software itself, or patches or auxiliary files, which are used to fix bugs or customize the software for use in particular situation. Open Embedded Core is elaborated on earlier and is an important set of validated metadata. Okay, now going back to recipes, a recipe will contain a list of settings and tasks for building packages, which are then used to build the binary image. A recipe describes where you get source code and which patches to apply. Recipes describe dependencies for libraries or for other recipes, as well as configuration and compilation options. They are stored in layers. It then creates a dependency tree to order the compilation, schedule the compilation of the included code, and finally execute the building of the specified custom Linux distribution. We can interpret a layer as a collection of related recipes. A layer is a repository containing relevant metadata that tells the open embedded build system how to build the target. Yocto project's layer model promotes collaboration, sharing, customization, and reuse in the Yocto project development environment. Layers logically separate the information of your project. Bitbake is a make-like build tool. Bitbake recipes specify how a particular package is built. They include all the package dependencies, source code locations, configuration, compilation, build, install, and remove instructions. Recipes also store the metadata for the package in standard variables. Related recipes are consolidated into a layer. During the build process, dependencies are tracked and native or cross-compilation of the package is performed. As a first step in cross-build setup, the framework will attempt to create a compiler toolchain suited for the target platform. Long word short, Bitbake plays the role of building system engine and is responsible for parsing metadata, generating task lists from it, and then performing these tasks. On the previous slide, you also saw Pokey, And going back to it, it is the name of the reference embedded distribution or reference OS of Yocto project. Pokey includes the open embedded build system or BitBake and open embedded core and the set of metadata that helps you to start building your own distribution. Pokey uses open embedded build system to build a small embedded operating system. And it's an integration layer on top of the OE core. Pokey provides the following: a basic level of distro infrastructure to illustrate how to customize the distro, a means to verify the Yocto project components. The use of Yocto project tools, you can download Pokey and use it as a bootstrap to your own distribution. Note that Pokey does not contain binary files. It's a full working example of how to build your own custom Linux distribution from source. The Yocto project has a development model for embedded Linux creation, which distinguishes it from other simple build systems. It's called the layer model. The layer model is designed to support both collaboration and customization at the same time. Layers are repositories containing related sets of instructions, which tells the build system what to do. Users can collaborate, share, and reuse layers. Layers can contain changes to previous instructions or sets at any time. This powerful override capability is what allows you to customize previous collaborative or community-supplied layers to suit your product requirements. Use different layers to logically separate information in your build. As an example, you could have a BSP layer, a GUI layer, a distro configuration, middleware, or an application. Putting your entire build into one layer limits and complicates further customization and reuse. Isolating information into layers, on the other hand, helps to simplify future customization and reuse. In the description of the video, we will provide the link for universally validated layers you can explore. Layers support the inclusion of technologies. On the link, you can find ones supported by Texas Instruments, STM Electronics, and even Intel. There is a collection of components and tools that are used by the project to maintain and update the actual project. They are also used directly by the project itself. Finally, other components and tools are used by developers to create their custom OSs. These components and tools are open source projects themselves or metadata. Both are separate from the reference distribution and build system, and most are downloaded separately. Now, this workflow diagram provides a high-level overview of what's going on during a Pokey build. The first step is to download the sources for the software that you are going to be building. We refer to this step as fetching the sources. Yocto Linux build supports standard methods such as download tar files from HTTP or FTP site. We can also download sources and apply all the necessary patches before build. Once the sources have been downloaded, they will be extracted and installed into temporary staging area. After the pre-selected binary format, packages will be generated. Once all the needed binary packages have been created, a binary package feed is generated, which then gets used to create root's file system image. Above the Beyond build system, there are also individual development tools that are maintained by Yocto project. Some are used by the project internally, and some needs to be developed. DevTools, or the cornerstone of the extensible SDK, is a command line tool called DevTool. This tool provides a number of features that helps you build, test, and package software within the extensible SDK, and optionally integrate it into an image built by the open embedded build system. The DevTool command line is organized similarly to Git, in that it has some number of subcommands for each function. You can run DevTool help to see all the commands. The DevTool commands that provide entry point into developments are DevTool add, which assists adding new software to be built, DevTool modify, which sets up an environment to enable you to modify the source of an existing component, and DevTool upgrade, which updates an existing recipe so that you can build it for an updated set of source files. The Extensible SDK, or ESDK, provides a cross-development toolchain and libraries tailored to the content of a specific image. The Extensible SDK makes it easy to add new applications and libraries to an image, modify the source for an existing component, test changes on how target hardware, and ease integration into the rest of the open embedded build system. You would use the Extensible SDK if you want the toolchain experience supplement with powerful set of DevTool comments tailored for the Yocto project environment. The next tool I want to discuss is CROPS, or Cross-Platform Enablement with Containers. It's an open source cross-platform development framework that leverages Docker container to provide an easily managed, extensible environment which allows developers to build binaries for a variety of architectures on Windows, Linux, and macOS hosts. Another great tool is Toaster. It's a web interface to Open Embedded and BitBake, the build system also used by Yocto. Toaster allows you to configure and run your builds and provides information and statistics about the build process. Toaster can be connected to Django and SQLite. With Toaster, you can browse and build any layers published in the Open Embedded Metadata Index, import your own layers for building, add and remove layers from your configuration, set configuration variables, select target or multiple targets to build, and start your own build.
Apart from inherent capabilities, the Yocto project has project features which are introduced in one release and generally expanded on and completed over the course of few releases. In-depth information about the features can be found in README files associated with releases and tools. This area provides high-level overview of feature updates to the third release and general project features as well. These features are binary builds, binary reproducibility, multi-configuration of several architectures, and etc. The Yocto project is an excellent choice for IoT projects. All the advantages discussed above are valid for designs in IoT space. There are, broadly speaking, two types of IoT devices: small systems hosting sensors or actuators, and large systems such as IoT gateways, network-attached storage boxes, home automation routers, and etc. Linux is likely overkill for small systems, as many of them use 8 or 16-bit microcontroller that cannot easily support Linux. For the larger devices, Linux is in general, and Yocto in particular, is an excellent option. For more and more, these types of devices are prototyped with easily available customer hardware devices such as Raspberry Pi and BeagleBone. The Yocto project has excellent support for these boards and many other similar boards, and is an excellent way to get started quickly on your IoT project. Another great advantage is that communication protocols such as MQTT and AMQT are already added into a Yocto build. Yocto project has some advantages and disadvantages. Advantages of Yocto project include flexibility, customizable. You can freely add components to it. It supports multiple architecture. Changing target architecture requires changing only one line in configuration, and you can build system for another architecture. Holds about 2 GB and leaves plenty of memory for data storage. You can build Yocto binary to be as small as 12 MB. Has industry and community support, and disadvantages of Yocto project are that it takes hours to build initially, hard to use without great programming skills and big expertise. It might take weeks to get known to project and understand how it works to start building and modifying your own system. The number of options for configuring your target can make it difficult to access the best choice and hard to detect where problem occurred. Yocto Linux has several alternatives. For example, Linear Ubuntu, which is ARM-centric Linux distribution based on Ubuntu core. With Linear, the industry can build in-home gear that runs cooler, faster, and smaller. Another alternative is Buildroot, which focuses on simplicity. The core Buildroot tool is kept as small as and as simple as possible, which makes it easy to use and understand. All special cases are handled in extensions, and Buildroot reuses existing tools like config whenever possible. Thus, learning Buildroot means learning tools that are applicable in other scenarios. The OS image Buildroot creates is also minimal by default, make builds fast. The projects provide a tangible difference in what they generate. Buildroot's output is root file system and nothing more. That's why sometimes it's called firmware generator. Whenever you need to update the system, you must regenerate the entire image or somehow build your own update mechanism. This restriction is by choice. The project believes embedded systems should not be updated like desktops and servers are, since the outcome of failed or partial update can be disastrous. Yocto project is a distribution. Specifically, it is a package feed, although providing a full-scale package management system for the target device is optional, and generally full disk images is certainly supported, but individual packages can be rebuilt as needed. While to change some package in Buildroot, it's required to build the entire system from start to finish. The Yocto project supports, in Yocto project, you can just modify package and rebuild only this package. Another alternative is Debian, which supports multiple architectures. It has huge software base and it's an attractive choice for all sorts of systems, but the main distribution is very much aimed at systems with at least desktop resources like hard disk and memory. Embedded Debian tries to strip Debian down to be a much smaller system while keeping all the good things. It is also an open development environment, and different methodologies are appropriate depending on the resources of the target system and the development environment. Embedded Debian exists to encourage work on all possible methods that build from Debian's current source tree or use its multi-architecture build tool. Embedded Debian is currently in development process, but plenty of people already use Debian in their devices. Another alternative is PTX dist. It's easy to use Linux distribution. This Linux distribution build the tool that allows you to compose your embedded Linux out of a huge set of standard components with a simple kernel-like configuration interface. Despite being rather simple in the basic configuration, PTX dist also allows you to perform truly complex and very fine-grained customizations of the packages and system configurations you need. It's something between Buildroot and Yocto. As you can see, developers have a variety of choices to build a Linux distribution and build systems. The Yocto project is a solid option for most embedded projects and serves as an excellent starting point. The benefits of Yocto build systems are we outlined benefits of Yocto build system, product development in the IoT space is proceeding at a blistering pace, and many of those devices have feature sets that benefit from Linux implementation. Yocto's wide variety of features, expandability, and fine-grained control over the content of target image makes it ideally suited for projects in these spaces, and is certainly worth some investigation as you start your own design.
Thank you for your attention.